Hello, good morning to all. Myself, Professor Ichapurak from Department of Botany, Ranchi Women's College. Today, I want to discuss about micrometry and karyotype analysis with the help of PowerPoint presentation made. Now, what is micrometry or micromeasurement? Micrometry is measurement of microscopic objects. For this, unit of measurement used is micron, mu m, micrometer, which is equal to 1 by 1000 millimeter. In order to measure microscopic objects, micrometers are used. There are two types of micrometers: stage micrometer and ocular micrometer. The stage micrometer is used to determine the value of one division of ocular for a certain microscope. The measurement of any object is possible with the help of ocular micrometer inserted into eyepiece of a microscope. Once the value of ocular micrometer for a microscope is determined at a given magnification, calibration is done. The measurement of any object or material is possible with the help of ocular micrometer only. Now let us know about the micrometers. Stage micrometer is a simple slide. In the center, a scale is present which is 1 millimeter divided into 100 divisions. Therefore, one division of stage micrometer is equal to 0.01 millimeter. That is, if changed into micron, is to be multiplied by 1000 will give rise to 10 micrometer. This you can see, this is the stage micrometer scale. Now this is the photograph of stage micrometer under 10x magnification, 10x objective, and this is under 40x objective. You can see it has bigger lines, and in between bigger lines there are 5 divisions, or altogether there are 100 divisions. The ocular micrometer has round cover slip like structure. In the center of this round glass also a scale is present having 100 divisions. After every 10 divisions, digits 10, 20, 30 up to 100 are marked. The value of one division of ocular is unknown and varies from microscope to microscope and also varies in different magnifications. Now this is the ocular micrometer. This is the scale present having 10, 20, 30, 40 like this. But the value of one division is not known. It has to be calibrated with the help of stage micrometer. Now what is the procedure of calibration? The stage micrometer is placed on the microscope below the objective and ocular micrometer is introduced into the eyepiece. By rotating the eyepiece, a scale of ocular micrometer is brought parallel to the scale of stage micrometer. The two scales are coincided at any point. The number of stage divisions between 10 ocular divisions is counted at 10x. This we will see in the next slide. 10 ocular division is equal to x division of stage micrometer. So 1 ocular division will be equal to x by 10 division of stage micrometer. that will be x by 10 into multiplied 0.01 millimeter, that is x by 10 multiplied 0.01 multiplied 1000 micrometer, that will be x micrometer. At low power, 10 ocular division is equal to 15 stage division for this particular microscope. So least count of the microscope at low power is 15 micron. In the same way, least count is calculated for high power. At high power 40x, 10 ocular division coincide with only 3.5 stage divisions, so least count is 3.5 micron. This is how the calculation is done. One division of stage is equal to 0.01 millimeter or 1 by 100 millimeter. 1 millimeter is equal to 1000 micron. 0.1 into 1000 will be 10 micron. So one division of stage is also equal to 10 micron. In low power, 15 stage divisions coincide with 10 ocular division. So the least count is 15 micrometer, and at high power it coincides with 3.5 division of stage micrometer. So the least count will be 3.5 micrometer. Now this you can see in this slide. You can see the ocular micrometer at 20 is being coincided with the stage, and you can count the number of divisions between 20 and 30, that is 1 big line, 2 big line, and 3, that is 15 stage divisions coincide with 10 ocular division. So the least count becomes 15 micrometer. And at high power, again you pay attention to the 20 of ocular division and come to 30, and if you count, there is 1, 2, 3, 3.5 stage division. So the least count is 3.5 for this high power magnification. For measurement of length and breadth of cells like Spirogyra, Udogonium, onion root tip cells, low power of microscope is used. The slide containing material is placed below objective, and ocular micrometer is introduced into eyepiece. By rotating eyepiece, ocular scale is brought parallel to the length of cell. At least 5 readings are taken and are averaged. Number of ocular divisions multiplied by least count gives length of cell in micron. In the same way, for measuring breadth, ocular is brought parallel to the breadth, and number of ocular divisions are counted and multiplied with least count. Now this slide shows the material, the slide, as well as the ocular micrometer, and you can count the number of ocular micrometer. When you want to measure the length of a cell, you can see in this high power between one end of the cell and two end of the cell. If we start counting, it will become 10, 15, 17 near about, like this. And in this way you have to take readings of 1, 2, 3, 4, 5 readings are to be taken, and then they are averaged, and the average is multiplied with the least count. On low power there are 15 divisions, 14, 12, 13, 16, and then it is multiplied with least count, and least count is 15, average is 14, so the length becomes 210 micron. In the same way, if the breadth is to be calculated, then the scale is to be brought parallel to the breadth of the cell, and number of division, ocular divisions are to be counted and averaged and multiplied by least count. This will give 15.0 micron. This I will show with the help of two slides separately also at the end. which will not be in the slideshow. Now, in this way, this is the photograph of the scale, and this is the photograph. With the help of scale and with the help of photograph of material and scale, the measurement can be taken, and this is for measurement of the chromosomes. A well scattered metaphase plate is focused under microscope. By rotating the eyepiece, ocular scale is brought parallel to each chromosome, and all chromosomes and their short arm and long arm are measured. To know the length in micron, the number of ocular division is multiplied by least count. Now, what is karyotype analysis? Some features of chromosome like number, size and centromeric position of individual chromosomes are rather characteristic of a given species. The term karyotype is used for characteristic chromosome complement of an organism. Karyotype represents the chromosome distribution of a cell of an individual. It deals with number of chromosomes, length of chromosomes, thickness of chromosome, position of centromere, presence of primary and secondary construction, and the size of satellite, etc., of the somatic chromosome complement. Generally, karyotype is prepared from well scattered chromosomes of mitotic metaphase plate. This we will see later on. For this, chromosomes are measured with the help of high power magnification of microscope or by camera lucida, having prism drawings of metaphase plate made on paper and also of stage micrometer on same magnification, or photomicrograph of metaphase plate, and also either of stage micrometer or ocular micrometer in the same magnification are taken, and then measurement is done. If photograph of stage micrometer is taken, then there is no need of multiplying with least count. But if ocular micrometer is taken, then multiply with least count. Meiotic prophase and metaphase are also studied to identify homologous pairs, bivalence, chiasma formation, their termination, recombination, etc. Each organism or species has characteristic number of chromosomes. As for example, Poissum sativum or P2N is equal to 14. In Allium cepa, it is 2N is equal to 16. Vicia fava or Bakla, it is 12. And in Lens culinaris or lentil, it is 14. Zygote and somatic cells are diploid, having two sets of chromosomes, which are contributed during fertilization by male and female gametes, which are haploid. Two chromosomes in diploid set are sex chromosomes or heterosomes, and others are autosomes. Some genera and species have more than two sets of chromosomes showing polyploid series. Triticum or wheat shows diploid count of 14, 28 and 42. Triticum monococcum, that is 2n is equal to 14, is diploid. Triticum dicoccum, 2n is equal to 28, is tetraploid. Whereas the wheat which we use commonly is Triticum aestivum, 2n is equal to 42, that is hexaploid. Triticum vulgare is also hexaploid. In all these, basic chromosome number X is equal to 7. Now let us know something about the human karyotype also. Human is Homo sapiens, and the 2n is equal to 46, having 46 chromosomes. The normal human karyotype contains 22 pairs of autosomal chromosomes chromosomes and one pair of sex chromosomes. Normal karyotype for female contain 2 X chromosomes and are denoted 46XX. Normal karyotype for males have an X and a Y chromosome and are denoted 46XY. Any variation from the standard karyotype may lead to development of abnormalities. Now this is the metaphase plate of human showing 46 chromosomes. Now let us see the human karyotype. It has many group of chromosomes like A, B, C, D, E, F, G. 1 to 3 lie in A group, having chromosomes which are large and metacentric. B 4 and 5 large submetacentric. C 6 to 12 and X chromosome medium size having submetacentric centromere. D is 13 to 15 medium sized acrocentric. E 16 to 18 short submetacentric. F 19 and 20 short metacentric, and G is 21 and 22 and Y chromosome short acrocentric. Now these are the two metaphase plates. This is male karyotype, so showing X chromosome and Y and 22 pairs of autosomes, and this is female karyotype showing 2 XX chromosome and 22 pairs of autosomes. Now let us come to see what we consider for karyotype analysis. For karyotype analysis, some of the following parameters can be taken, like total length of individual chromosome TLIC in micrometer, arm ratio R or index to centromeric position, then centromeric index, index to relative length of chromosome, relative chromosome length, thickness of chromosome, average chromosome length or mean chromosome length, total chromatin length of haploid complement, total chromatin volume of haploid complement, F percentage, total form percentage or TF percentage, symmetry or S percentage, karyotype category KC by as proposed by Stebbins 1971, then karyotype formula or the presentation, and ideogram or karyogram is the graphical presentation of the chromosome complement. Now total length of individual chromosome, it is measured in micron and includes length of both arms and centromere from one telomere to another telomere. The chromosomes are grouped variously on the size of chromosome as per the researcher, as per the size of chromosomes in his or her material. Now we can categorize chromosomes as large, medium, small, minute. According to one category, if chromosomes are from 5 micron to 10, they are considered large, 3 to 5 medium, 1 to 3 small, and lower than 1 is minute. In this way, many categories can be taken. Arm ratio or index to centromeric position. Arm ratio, it is the ratio of long arm and short arm of chromosome. Classification of chromosomes on arm ratio is made as per Levan 1964. Value of arm ratio can range from 1 if short arm is equal to long arm to infinite. Limit for short arm is 0. You can see in this table, for absolute median it is 1, for median 1.01 to 1.7, for submedian 1.71 to 3, and from 3.01 to 7 it is subterminal, and more than 7.01 to infinity it is terminal. Then it is continued. Index to centromeric position can also be taken as short arm by long arm, which was first proposed by Battaglia 1955. It is reciprocal to the arm ratio. Its value can range from 1 if short arm is equal to long arm to 0 if short arm is equal to 0. It is the ratio of short arm to long arm of a chromosome as proposed again by Sava 1965 in Karyotyoe, and according to this the chromosomes can be with median centromere, submedian centromere, subterminal and terminal, having the ratio 1, 0.5 to 0.99, less than 0.49 and 0. And the chromosomes are known metacentric, submetacentric, acrocentric and telocentric. Now we can see the chromosomes which are metacentric, submetacentric, acrocentric and telocentric, and in case of submetacentric uh, centromeric position there will be a short arm and there will be a long arm. Short arm is also known as PR and long arm is known as QR. So they are called P and Q, and centromeric index, that is equal to S divided by L plus S. It is the proportion of short arm in respect with whole chromosome. Its value can range from 0.5 if S is equal to L to 0 if S is equal to 0. Complementary to centromeric index can also be L divided by long arm divided by long arm plus short arm. It is the proportion of long arm in respect with the whole chromosome. Its value can range from 0.5 if S is equal to L to 1 if S is equal to 0. Index to relative length of chromosome. It is ratio of length of each chromosome to mean length of complement, and according to it there are 4 types of chromosomes: small, medium small S, medium small M1, medium large M2 and more than 1.25 it is known as L. Relative chromosome length RCL, it is the ratio in percentage between total length of individual chromosome and total chromatin length of haploid complement. RCL is equal to TLIC divided by total chromosome length into 100. Now thickness of chromosome. Chromosomes are classified into 3 categories on the basis of thickness of chromosomes, like slender if it is less than 1 micron, moderately thick it is 1 micron, and thick if it is more than 1 micron. Average chromosome length is the ratio between total chromatin length of haploid complement and total number of chromosomes in haploid set, that is the mean chromosome. Total chromatin length TCL is the sum total of length of all chromosomes of a complement of haploid set, summation chromosome length. Total chromatin volume TCV, total chromatin volume of haploid complement is the sum total of chromatin volume, which can be calculated as pi r square L, chromatin volume, that is summed up. F percentage is the ratio in percentage of short arm length to entire chromosome length. F percentage, short arm length of chromosome divided by length of chromosome into 100. Then there is another terminology known as total form percentage, TF percentage. It is a ratio in percentage of total sum of short arm length to total chromatin length of the complement as advocated by Fujiwara 1962. TF percentage is equal to total length of short arm in a chromosome set divided by total length of chromosome set into 100. Symmetry S percentage, it is the ratio in percentage of total of length of shortest chromosome to the length of longest chromosome of the complement, and is calculated as follows: S percentage, which is also known as GI or gradient index, length of shortest chromosome of the complement divided by length of longest chromosome of the complement into 100. Now let us see what is karyotype category. A karyotype exhibiting large difference between smallest and largest chromosome and fewer metacentric chromosome is asymmetric, which is believed to be an advanced feature over symmetric karyotype, in which less difference between largest and smallest chromosome and more chromosomes are with metacentric centromere. Karyotypes have been classified into 12 categories, that is 1A to 4C as per Stebbins, which we will see on the next slide, taking into account both the degree of difference between largest LC and smallest SC chromosome of the complement and position of centromere on chromosome. He established these by recognizing 3 degrees of difference A to C between largest and smallest chromosome of the complement, and 4 degrees 1 to 4 with respect to the proportion of chromosomes which are metacentric, with an arm ratio of less than 2:1. Now this table shows the type of chromosomes or chromosome karyotype categories, that is 1A, 2A, 3A, 4A, 1B, 2B, 3B, 4B, 1C, 2C, 3C, 4C, depending on the longest chromosome and shortest chromosome ratio, and also on proportion of chromosomes with arm ratio less than 2:1 on the centromeric position. In this, 1A is the most primitive and 4C is the most advanced. The karyotype of 1A category of Stebbins are the most primitive, having less difference between largest and smallest chromosome and less number of chromosomes with asymmetric centromeric position, that is SM, ST, T, and more with absolute median and median centromeric position as per Levan et al. 1964, whereas 4C category of Stebbins is most advanced, having large difference between largest and smallest chromosome and more number of chromosomes with submedian, subterminal and terminal centromeric position. Karyotype asymmetry, the concept of karyotype asymmetry versus karyotype symmetry versus asymmetry was developed by Levitsky 1931. The information about karyotype asymmetry has been known to be significant in plant taxa, where association occur between increasing asymmetry of karyotype and other characteristics such as chromosome number, plant morphology or plant habit. According to Stebbins 1971, increasing asymmetry occurs through pericentric inversion, changing median centromeric position to subterminal one. You can see here the pericentric inversion takes place in the segment EF, EFGH. It becomes inverted HGFE and it becomes subterminal. Now these are the karyotypic details of a taxa under observation of lens culinaris. Variety is L4149, n is equal to 7 and 2n is equal to 14. Karyotype. Now on the basis of this data, the karyotypic formula, which illustrate type of chromosome and size and index of centromeric position of the chromosome complement, the karyotypic formula becomes 1 median, 2 submedian, 3 chromosomes are of B type and 4 chromosomes are C type, having 3 chromosomes with median centromeric position and 1 with submedian centromeric position. The largest chromosome is 6.80 and the smallest chromosome is 3.40. Now let us see what will be the karyotype category according to this data and how will the ideogram will be formed. The chromosome complement reveals that chromosome length ranges from 3.40 to shortest chromosome to 6.80. Karyotype reveals 4 pairs with median and 3 pairs with submedian centromere. The total chromatin length is 68 micrometer of haploid set and 34.0 of haploid set or diploid set. Average chromosome length is 4.86 micrometer. Longest chromosome and shortest chromosome ratio is 2.0 and P ratio, number of chromosomes with submetacentric centromere divided by total number of chromosomes is 3 by 7, that is 0.42. According to this, the karyotype category as per Stebbins become 2p. Now, ideogram or karyogram, it can be presented graphically by arranging the chromosomes in descending order of length in a straight line. The longest chromosome is placed on right side and smallest on left side. All chromosomes in a complement do not bear the centromere at the same position. While in graphical representation, either the position of centromere is fixed at a point or are located on different points and one telomere of chromosome is fixed. With that we will see in the next slide. SAT chromosomes are represented by small break on the arm which belongs it and a scale is taken as per example 1 centimeter will represent 1 mu. So a chromosome having 4 micrometer length will cover 4 centimeters, 4 squares of graph paper, and if it has median centromere then 2 centimeters above and 2 centimeters below. The gap represents the centromere. Now you can see this slide. This slide shows the metaphase plate of the material whose data has been shown, outline drawing and the ideogram. In this the centromeric position has been fixed and a scale 2 micrometer is taken. In the lower the telomere has been, one of the telomere has been fixed, so centromere comes as it is. This ideogram has a haploid chromosome number n is equal to 9 and this has haploid chromosome number n is equal to 7. Now these are the metaphase plates and karyogram of Pisum sativum. This is the karyogram of Vicia fava and this is how on graph paper the ideogram can be prepared, taking the graph paper and the largest chromosome on one side and the smallest chromosome on other side. In this centromeric position has been fixed. It is ideogram of haploid set having n is equal to 6 of Vicia fava. Now this slide represents the metaphase plate, its outline drawing and karyogram of Cara fibrosa having n is equal to 56. Now these are some of the metaphase plates. Now karyotype asymmetry, after Stebbins also some work has been done. 3 additional parameters have been added after Stebbins 1971 formulation of 12 categories of karyotype. Some additional parameters were later on added related with karyotype asymmetry by Pastko 2006 and Peruzzi and Iroglu 2013, which are coefficient of variation of chromosome length CVCL, that is SCL divided by XCL into 100, that is A2 into 100, a measure of interchromosomal asymmetry, which was given by Pastigo 2006. Mean centromeric asymmetry MCA, that is mean L minus S divided by L plus S into 100 or A into 100, a measure of intrachromosomal asymmetry. It was given by Peruzzi and Irogli 2013. Coefficient of variation of centromeric index CVCL CVCI divided by XCI into 100, a measure of centromeric position heterogeneity in the karyotype by Pastigo 2006. CVCR is the ratio between standard deviation and mean of sample into 100. This parameter ranges from 0 to 100, no variation. MCA, mean centromeric asymmetry, where centromeric asymmetry of a single chromosome is given by the formula L minus S divided L plus S. Accordingly, MCA is equal to A into 100, and CVCI is offered that precisely assesses the relative variation in centromeric position in a complement. These three parameters have the potential to display even minor karyotypic variations. Now these are the references, and I also want to contribute or make the students aware about some computer aided programs or software which have been developed from time to time for measurement of chromosomes, short arm and long arm, with the help of images uploaded on the computer in bitmap form or in JPEG form. Measurements can be done, and these softwares are Micromeasure, which can be downloaded from this website, Colostate AGU Micromeasure. Karyotype can be downloaded from this software, this website, and an ideogram constructing and karyotype analyzing software. This software and related documentation is freely available on the website of University of Kurdistan on their website. If someone is interested, can go through and try to analyze and make ideograms using digital images. The references are also given. Now with this, I have explained about the karyotype analysis and micrometry, and I would like to add uh, two more slides. How to measure. I'll take to measure. Now with the help of this slide, these two slides, we can it can be shown that how measurement can be done. In this slide we can see there is ocular scale and also the photograph. Now this scale can be brought, the photograph of the scale can be brought very close to the length of the cells, and number of divisions, ocular division, can be counted from one end of the cell to other cell. In this way 4 to 5 readings can be taken and averaged. Now in the next slide, this is for measurement of the chromosomes. A well scattered metaphase plate is focused under microscope by by picking up the scale. This scale can be brought very close to the chromosomes and can be brought very close to the chromosome, and the length of long arm and short arm can be measured. The ocular divisions can be counted. In this way, karyotypic analysis can be done with the help of photograph of the metaphase plates as well as the photograph of the scale. Now, suppose this is the chromosome having this is the long arm and this is the short arm. So the scale can be brought parallel to the long arm, then the scale can be brought parallel to the short arm like this, and the number of ocular divisions can be counted and the scale can be brought away. In this way, uh, it can be uh, done. Now, in this way, karyotype analysis is a tough work under the microscope. There are many options which can be used for karyotypic analysis, as with the help of camera lucida drawing of the plate as well as camera lucida drawing of the scale on the same magnification, or with the help of photograph taken and photograph taken of metaphase plate and of the scale on the same magnification. Now with this, I think the students must know how to um, study the karyotype analysis. Thank you. Now I want to end the and